Hello everyone, welcome to my channel Cherish Physics. Subscribe my channel and keep watching. In this video, I am going to cover up to LISSAJOUS figures. The topic simple harmonic motion covers so many important terms and equations. Even though I am uploading this video for exam point of view, I have given so many important definitions. Let's get into the topic oscillations. It is of two types, periodic motion and non-periodic motion. First one, periodic motion. Any motions which repeats itself in a fixed time interval is known as periodic motion, and some examples I have given. The first one, motion of planets around the sun, hands in pendulum clock, swing of a cradle, waxing and waning of moon, etc. And next one, non-periodic motion. Any motion which does not repeat itself after a regular interval of time is known as non-periodic motion. The examples are occurrence of earthquake, eruption of volcano, etc. If you know any other examples, comment it in the text box. Next, oscillatory motion. By the term oscillation, we very well know its meaning. A back and forth motion of a particle or an object about its mean position, that is said to be oscillation. The main examples are vibration of a string, vibration of a tuning fork. See the note, it is a very important one. The first point, all oscillatory motion are periodic, whereas all periodic motion need not be oscillation in nature. What these lines defines means, oscillatory motion is a to and fro motion about the mean position and they are said to be periodic. But some examples like motion of the planet around the sun, it is also periodic, but it doesn't to and fro motion about the mean position. Second point, a simple harmonic motion is a special type of oscillatory motion, but all oscillatory motions need not to be simple harmonic. Why all oscillatory motions need not to be simple harmonic means, simple harmonic motion obeys some mathematical equations, but oscillatory motion doesn't. Here are some definitions which is strictly followed by simple harmonic motion. The first one, a particle is said to execute simple harmonic motion if its acceleration is always directly proportional to its displacement from its mean position and is always directed to the equilibrium position, that is mean position. A is proportional to minus x. Here the negative sign implies the direction because the restoring force of the object always points back towards the mean position. Just imagine the simple pendulum. We can easily understand the concept, that is, the force acting on the oscillating body is always in the direction opposite to the displacement of the body from the equilibrium position. Restoring force F is proportional to minus x. Similarly, for a spring mass system, that is, the top end is connected to the clamp and in the lower end we are going to apply the load. And if you just pull the load and release it, the spring gets oscillates. It executes simple harmonic motion. According to Hooke's law, the restoring force is directly proportional to the displacement of the spring, that is, F is equal to minus kx. In the acceleration equation, let us take the proportionality constant as omega squared, where omega is the angular frequency of simple harmonic motion, hence A equal to minus omega squared x. And by Newton's second law, F is equal to ma. Substitute the value of A here, which is equal to minus m omega squared x, and this is Hooke's law equation, F is equal to minus kx. Now by comparing the Newton's law equation and Hooke's law equation, we get k equal to m into omega squared. The term k is called the force constant or spring constant or stiffness constant. The SI unit of force constant is Newton per meter. These are some important points. Note down it. First one, a harmonic oscillation of constant amplitude and single frequency is called simple harmonic motion. And already we know simple harmonic motion is the special case of oscillatory or vibratory motion, and its examples are motion of a simple pendulum, vibrating tuning fork, spring mass system. Simple harmonic motions are expressed in terms of sine or cosine functions. The oscillatory motion in a physical system results from two properties, that is, property of inertia and property of elasticity. Why these two properties are the pillar of simple harmonic motion means, only due to inertia and elasticity the object moves to and fro continuously about its mean position. Now let us see the characteristics of simple harmonic motion. We have already seen so many points. It is given as the characteristics. First point is the motion is periodic. Second point, the motion is along a straight line about the mean position or equilibrium position. Third point, the acceleration is proportional to displacement. And fourth point, acceleration is directed towards the mean position. Next, Let us see the force versus displacement graph. It is a straight line passing through the origin with negative slope. So, the line passes through second and fourth quadrant. In the second quadrant, the displacement is positive and F is negative. And in the fourth quadrant, the force is positive and the displacement is negative. From the slope, we get the negative reciprocal of the force constant. And next is the important concept. The projection of uniform circular motion on a diameter is simple harmonic motion. See the first diagram. P is a particle which moves on the circumference of the circle. That is, if it starts from X and it moves on and reaches Y, then to X dash and then to Y dash, and then it comes to the point X. Even though the particle P moves on the circle, its footsteps falls on the diameter line here along the y-axis. If the particle is at the point P, it covers the displacement OM and the maximum displacement is OY in the positive axis and OY dash in the negative axis. It is clearly given in the graph. The displacement equation y equal to a sin omega t. The particle completes one full cycle in a circular motion, then it is said to complete one vibration, that is a simple harmonic motion. In the last slide, we have seen the displacement equation y equal to a sin omega t, and now let's see velocity in simple harmonic motion. Velocity is the rate of change of displacement, and by derivation we get the formula v equal to omega into root of a squared minus omega squared. And v is the velocity, omega is the angular frequency, a is the acceleration, and y is the displacement. Now imagine the simple pendulum. In the mean position, the displacement is 0 and the velocity is maximum, that is v is equal to omega a. In the extreme position, the displacement is maximum, that is y equal to plus or minus a, that is on both sides. And at the extreme position, the velocity is 0. That is, at the extreme position, the simple pendulum bob stops a moment, that is, at that point the velocity is 0 and then it starts oscillation. So, in the mean position, the velocity is maximum. In a simple word, it is said as the displacement increases from 0 to maximum, though the velocity decreases from maximum to 0 from the equilibrium position. And next is the acceleration in simple harmonic motion. It is the rate of change of velocity, and by derivation we got the formula for acceleration as a equal to minus omega squared y. Let's see the special case. At the mean position, the displacement is 0 and the acceleration is also 0. And in the extreme position, the displacement is maximum, that is y equal to plus or minus a, and also the acceleration is also maximum, that is minus or plus a omega squared, because acceleration is directly proportional to the displacement in the negative direction. This means if the object is displaced to the right side, the acceleration pulls the object to the left side towards the mean position. Here I have given it in the simple form. See the diagram and understand that in the mean position and the extreme position, how the quantities and displacement, acceleration, speed, kinetic energy and potential energy varies. Surely question may ask in this, like match the following or statement type questions. Next is the important terms in simple harmonic motion. First time period, t is equal to 2 pi by omega, and frequency n equal to 1 by t, then angular frequency omega equal to 2 pi n, and the unit of angular frequency is radian per second. Next one phase, it is implied by the letter phi. It is the state of the particle as regard to its direction of motion and position at any instant of time. That is, it is the phase angle. In the displacement equation, y equal to a sin omega t plus phi naught, the term omega t plus phi naught is the phase and is denoted by the letter phi. Next one, epoch. It is the initial phase of the vibrating particle, that is the phase at time t equal to 0. So in the above equation, substitute that, we get phi equal to phi naught. That is, epoch means it is also the phase angle at time t equal to 0. Next, examples of simple harmonic motion. We have seen so many examples yet, but let's see the types. The first type is linear type of simple harmonic motion, and its example is spring mass system, and the condition is F is proportional to minus x or A is proportional to minus x. Then angular type of simple harmonic motion. The examples are vibration of a simple pendulum, torsional pendulum, etc. And its condition is tau is proportional to theta. The tau is the torque and theta is the angular displacement. Next is the important topic, combination of two simple harmonic motion in a straight line. Imagine two tuning fork vibrates simultaneously in a straight line and the vibration gets superimposed. Recall the general formula of simple harmonic motion. Y equal to A sin omega t plus phi, and let the composition of two simple harmonic motion which has same frequency acting along the same straight line, it results a new simple harmonic motion which also has the same frequency, but its amplitude and phase angle is determined by the superposition of the individual amplitude and their phase difference. The displacement equation for the first simple harmonic motion is y1 equal to a1 sin omega t plus alpha 1, and for the second one y2 equal to a2 sin omega t plus alpha 2. The resultant motion y equal to y1 plus y2. By adding and expanding the above two equations and compare it with the general equation, we get the amplitude A and the phase angle phi of the resultant vibration, and it is A squared equal to A1 squared plus A2 squared plus 2A1 A2 into cos alpha 1 minus alpha 2, and the phase angle tan phi equal to A1 sin alpha 1 plus A2 sin alpha 2 divided by A1 cos alpha 1 plus A2 cos alpha 2. These two equations are very important points in this topic. Now let's see its special cases. The first case, phi is equal to 0, that is in phase. If we put phi is equal to 0 in the amplitude equation, because phi is equal to alpha 1 minus alpha 2, so cos 0 which is equal to 1, the equation becomes a squared equal to a1 squared plus a2 squared plus 2a1 a2. This is a plus b the whole squared formula. So a equal to a1 plus a2, it is said to be maximum amplitude. And in the second case, let us take phi equal to 180 degree, that is out of phase. Cos 180 is minus 1. The equation implies a1 minus a2 the whole squared formula. Hence a equal to a1 minus a2, that is minimum amplitude. There's one important point. If two motions have different frequencies, then the resultant motion is complex and it is non-simple harmonic motion. Next topic, combination of two simple harmonic motion at right angles. Here, imagine a simple pendulum which is in the ship. The ship is moving forward. While disturbing the bob, it oscillates. Also, the ship flips sideways. It introduces a lateral oscillation in the bob which is perpendicular to the vertical oscillation of the simple pendulum. Hence, the resultant path of the bob is the vector sum of the two perpendicular motion. Let us take the equations of displacement along the x-axis and y-axis as x equal to a sin omega t plus alpha and y equal to b sin omega t. Here note down the point, the two vibrations acting are of the same period but of different amplitude and different phase angles. Here I have given the final equation which is x squared divided by a squared plus y squared divided by b squared minus 2xy divided by ab into cos alpha, which is equal to sin squared alpha, and this equation represents the general equation of an ellipse. Actually, if we combine a two simple harmonic motion at right angles, means its pattern is either symmetric or non-symmetric, and that figure is said to be LISSAJOUS figures. Now let us see what is LISSAJOUS figures. It is the graphical pattern that results from the combination of two simple harmonic motion acting at right angles to each other. That is, it is the curve traced by the motion. Its visual path we can see in the CRO. The cathode ray oscilloscope. Mainly, the symmetric and non-symmetric nature of LISSAJOUS figures depends upon the frequency ratio and the path difference. With the help of LISSAJOUS figures, we can determine the ratio of the time period of oscillations, and it is used to compare the amplitude, frequencies and phase of the simple harmonic motion. Let's see some special cases of LISSAJOUS figures. Let us take the general equation x squared divided by a squared plus y squared divided by b squared minus 2xy divided by ab into cos alpha, which is equal to sin squared alpha. Mainly, the resultant vibration of the particle depends upon the value of alpha, phase angle. Let the first special case, the phase angle alpha equal to 0 or 2 pi, then cos alpha, that is cos 0 which is equal to 1, and sin 0 which is equal to 0. Substitute the cos alpha and sin alpha value in the above equation. We get x squared divided by a squared plus y squared divided by b squared minus 2xy divided by AB, which is equal to 0. And this is in the form x divided by a minus y divided by b the whole square, which is equal to 0. Then which implies x by a, which is equal to y by b. Therefore, y equal to b by a into x. It implies the equation y is equal to mx plus c. This straight line equation, the term c, which is equal to 0 here because the line passing through the origin. See the graph along the pink line. The resultant motion of the particle will move with a positive slope. In the second case, let alpha equal to pi, that is 180 degree, cos 180 degree is minus 1 and sin 180 degree is equal to 0. Hence, the above equation becomes x squared divided by a squared plus y squared divided by b squared plus 2xy divided by ab, which is equal to 0, which is in the form x by a plus y by b the whole squared, which is equal to 0. This implies x divided by a, which is equal to minus y divided by b. Therefore, y equal to minus b by a into x. In this case, the slope which is in the second and the fourth quadrant, so it gives a negative slope. Third one, let alpha equal to pi by 2, cos pi by 2 which is equal to 0 and sin 90 which is equal to 1. Hence the equation becomes x squared divided by a squared plus y squared divided by b squared, which is equal to 1, and this implies the equation of ellipse. Here in the ellipse, a and b implies the semi-major and semi-minor axis of the ellipse. And fourth case, alpha equal to 90 degree, cos 90 equal to 0 and sin 90 equal to 0. Here let one more condition, a equal to b, which is equal to r. By substituting these in the above equation, we get the equation as x squared plus y squared, which is equal to r squared. This implies the equation of a circle where r is the radius of the circle. So here the two simple harmonic motion which is perpendicular to each other, then the resultant vibrations of the particle. See the graph which moves along the circle. Fifth case, alpha equal to pi by 4, that is cos 45 degree, which is equal to 1 by root 2, sin 45 degree, which is also equal to 1 by root 2. By substituting these in the above equation, we get x squared divided by a squared plus y squared divided by b squared minus 2xy divided by root 2 into ab, which is equal to 1 by 2. This implies the equation of oblique ellipse of axis A and B. In all the 5 cases, we get symmetric pattern of LISSAJOUS figures because its frequency ratio is 1:1. Here I have given some special cases of LISSAJOUS pattern. First, the frequency ratio is 1:1 and its phase difference is 0 degree, means we get the figure as a straight line with positive slope. Second one, the frequency ratio is 1:1 and its phase difference is 90 degree. We get a circle or ellipse which depends upon the amplitudes A and B. If it is equal, we get a circle. If it is not equal, we get ellipse. Third one, the frequency is 1:1 and phase difference is 180 degree. We get the LISSAJOUS pattern as a straight line with negative slope. And the fourth case, the frequency ratio is 1:2 and phase difference is 0 degree. We get the LISSAJOUS figure as a figure 8 pattern. Fifth one, the frequency ratio is 1:2 and the phase difference is 90 degree, means we get the LISSAJOUS figure as a asymmetric figure 8 pattern. Last one, the frequency ratio is 2:3 and the phase difference is 0 degree. The LISSAJOUS figure pattern is more complex with loops. Thank you.